Okay, so today's lecture is focusing on the probabilistic interpretation of CFS. It's not quite the zeta function, but it's this completed zeta function. And it seems to me that people have discussed probabilistic interpretation of the Riemann zeta function in various contexts. Let me just refresh your memory. Here's a question. These are kind of elementary number theory problem. What is the probability that GCD of N1, N2, and K is equal to N when the Ni's are randomly chosen. This is a classical question. So clearly, the problem can be reduced to the statement that writing let me not do it like this. Well, okay. Writing n n1 equals n times m1, n2 equals n times m2. Etc. It reduces to the problem of what is the probability that M1, M2, and K are randomly chosen and GCD of M1 and K is 1. So if I choose M1 to MK randomly, and I ask how often, what is the probability that this happens? Well, you all know that in order to filter out GCD, you use the Mobius function. So we need to count the number of MIs, let's say, in a box, H, 1 up to K, such that the GCD, the divisors of all the MIs, you want the GCD to be 1. So this thing will ensure the GCD, if the GCD is 1, it'll give you 1, otherwise it gives you 0. So this we have. And so this rearranging this, you get that D is less than or equal to H. Mu D, and then you're counting numbers less than H, so that D divides MI, and you're doing this for 1 up to K. So
this notation means you want all the divisors of MI.
D divides M1, D divides M2, dot, dot, dot. That's what it means. So D divides all of them. That's what it means. And so if you do that, then of course you end up getting summation D divides D less than H mu D. And then each of these MIs are independent inside. You're counting how many things are in a box, divisible by D. So this number is nothing but H over D to the power K. And so if I look at how many elements are there in my box, well, H choices for each slot and H to the K thing. So in other words, the probability equals the limit infinity, 1 over h to the k times this summation d less than h mu d h over d to the k. And now removing this square brackets, it's easy to see that this is just simply 1 over zeta k. And then if you want the probability that GCD of k randomly chosen elements to be n, then equals, this equals 1 over zeta k n to the k. So this is in line with that principle summation of any sequence adding up to 1, that you have a probability distribution. So this problem of counting how many tuples have GCD n is given by this, what is often called the zeta distribution. Now, for a long time, I have also fallen into this trap of trying to study this zeta distribution. Of course, I even had a postdoc who, well, didn't take up the suggestion actually. Anyway, you could change the k to s, a real number s, and ask, is there a model? Of course, you can't talk about s tuples anymore because it doesn't make any sense. Can you talk about what is a model in which 1 over zeta s, 1 over n to the s, zeta s is the probability of the event, of a certain event, and that will model this distribution. And it's possible to construct that, and I toyed with that for a while, thinking that it might lead to some understanding. But this is interesting. This actually was a problem that Giancarlo Rota and I was working on, and we got something. And it's nice and interesting combinatorially, but from a number theory perspective, it doesn't make any dent. So this is interesting, and it seems that the real focus of attention should not be zeta s, but it should be xi of s. Remember what xi of s was? It's a completed zeta function. So, and this is in line with the, Langland's philosophy, or Artinian. Actually, it goes back even before Langland's. Goes to Artin. And so recall that C of S was equal to 1/2 Ss minus 1 pi to minus S over 2 gamma S over 2 zeta of S. So you've actually completed the zeta function. And we proved yesterday the functional equation and we also had C of S equals 0 to infinity of theta of y minus 1, and I think there was a 2 here, to y to the s dy over y. Theta of y is minus infinity to infinity e to the minus pi m squared y. This was a theta function. So we proved that last. Now, what I'm going to do is I'm going to do a calculation of polya, and which leads to a probabilistic interpretation of C of S. So you see, this is so this example that I gave you, this baby example, kind of shows you that this fixation on Riemann zeta function in this fashion is limits one's view. And as I said, I was also, and it's interesting. It's another story. This zeta distribution, not for these lectures, but certainly of interest in its own right. Like you can think of like the zeta version of the Poisson distribution. Somehow you're trying to model these numbers as probabilities. But it's interesting in its own right. So the first thing we will do is we will put g of y equals theta of y squared. Then recall the functional equation for the theta function that was proved yesterday using the Poisson summation. Poisson summation formula. We proved this last time. So what does this mean for g? Well, g of 1 over y is theta of 1 over y squared is equal to y theta of y squared, which is g of y. So you have this functional equation for g, which gives you the, right? And what we will do now, this is why I need a cheat sheet. Okay, so this, so if I change y to y squared here, so I can try to write Cs as a Mellon transform of the g function, then what happens? In star, put change y to y squared. Okay. Then what happens? Do C of S theta of y squared is g of y. Keep in mind what this 1 is doing. The 1 is, because the theta function has n equals 0 term, it's divergent. It makes the thing divergent. You can't integrate 1 from 0 to infinity, right? So you subtract 1 and everything is exponential decay. So that's what's going on here. Now I got to change this to y to y to the oh, wait a minute. Now this was there's an s over 2. Sorry. There was an s over 2 before the previous calculation. So this becomes now y to the s. And then, interestingly enough, if you change y to y squared, you'll find that this is still dy over y. Work it out. So we have, from here, we have this formula. Now, we're going to make one more transformation, and the transformation, as I said, I didn't come up with this. This is Polya. Is put. I know what I can now. Once I understand it, I can explain after the fact why he did this. But it's certainly not.
So 2 gets cancelled, I guess.
Yeah.
2 gets cancelled. Thank you.
Yeah.
That's, 2 gets cancelled.
Yeah.
This is a 2 coming from dy by y square. From dy by y, if you put some w is equal to y square, I think you will get a 2.
Or you wanted no one
was not C of S, it was pi to the minus S over two gamma S over two zeta S. So I have to divide by SS minus one. See, if you remember
Okay.
the original, I have to divide by SS minus one here, okay? Now, what are you saying here? So there's a
That two will.
SS minus one, you think the two goes away?
Yeah.
Let me think, so if I put,
You introduced the half in Z of S, that was artificial, that is something that you did. Maybe
Yeah.
that has to do something.
no, that, now I removed it. No, that's going to be important, leave it there, okay? So you've got two there. I think this is pi to the minus S over, this is okay. And then now what are you saying? You're saying that if I change y to y squared,
Yeah.
let's see, what happens, so that becomes y to the S.
Two
and
y
then
dy
two y dy
divided by
divided by
y square.
y squared. And then there's a two, and you're saying there's nothing there?
Yeah.
Okay, maybe that's right. I mean, from this point of view, it's right. Let's just try to get to the punchline. So put h of y to be this crazy combination. Doesn't look motivated. And of course, this can be rewritten as d by dy of y squared g prime of y. Okay? Now, let's keep in mind that we have theta of y is this, g of y is minus infinity to infinity of e to the minus pi n squared y squared. Okay. And so I have in this expression for h of y, I have g prime of y and g double prime of y. And I'd like to look at how it affects these terms. So g prime of y is equal to what? I differentiate this thing with respect to y. And what do I get? Minus 2 pi n squared y, correct? That's what I end up getting. Somebody had a question? I can't hear.
Sir, it is pointwise convergent at y is equal to 0?
Well, no, it's y is always positive. Yeah, y is always positive in this game, okay? Now, let's take the second derivative, because that's what we need in this thing, calculation. And so what is that going to be? Well, it's going to be e to the minus pi n squared y squared. To differentiate that again, so it's going to be minus 2 pi n squared y squared plus, or maybe minus, plus e to the minus pi n squared y squared times the derivative of this thing, right? It's a minus 2 pi n squared. So let's write this up cleanly. G double prime of y equals minus infinity to infinity of something e to the minus pi n squared y squared, and 2 pi n squared y. Sorry, 2 pi n squared y squared, so it's what, 4 pi squared. Hope everybody's checking my calculations. Looks okay?
Shouldn't it be plus 2 pi n squared?
I just rubbed it off. What did I do?
No, correct.
Is it okay? All
No,
right.
there was minus in both the terms, he took the minus out.
So, no, it was in the first term it was a minus the whole square. So,
No, no,
now
he
what
has
is-
taken minus.
I think outside minus would be there.
I mean the minus in the summation, beginning of the summation should not be there.
Yeah, outside the summation minus will be there.
Yes, sir, yes, sir.
Remove it?
Yeah.
Okay. Okay. Now, this combination h of y is given by this, so h of y is this 2y g prime of y, which is here, plus y squared g double prime of y, which is here. So I'd like to see the expansion. I'm just going to write the answer down. Now, oh, by the way, what the advantage of this derivative, and this is, I think, is Polya's motivation. The advantage of the derivative, this problematic n equals 0 term here, which gives rise to 1, he wants to eliminate it. So by taking the derivative, you eliminate it. Because by taking the derivative, you end up getting these n's. So I think, at least I think this is the motivation, part of the motivation for this combination. You may ask, how do you get this silly thing? Well, and then this is going to work. I think this is one of the reasons, so let me just write down the answer. So we're now starting from n equals 1 to infinity, because these n equals 0 terms, there's nothing there. So when you take that, and you double it, of course, then I am getting 2 pi squared n to the 4th y squared minus 3 pi n squared e to the minus pi n squared y. So starting from this simple object, Polya decides he wants to use this, which is more complicated looking, but there's a good reason for it. Now of course, so on one hand it's this, and therefore we've calculated its, this expansion in terms of these exponentials. On the other hand, we have this. And his question now is, what is the Mellon transform of h of y? Well, from this piece here, so I think everyone knows what to do now. Next. Right. You have an integral like this, you'll integrate by parts. Because obviously you know how that works. Y squared g double prime of y to the s minus 1, 0 to infinity, minus the integral to infinity, y squared g double prime of y times the derivative of y to the s minus 1, which is s minus 1, obviously this is, I know the integral in this. You get that? And then everything else is y s minus 1, put that there, and then take the derivative. And what's the point about this? Notice the g double here, g double prime of y at infinity is 0, because there is no n equals 0 term here. It's all exponential decay, and I'm going to plug in y equals infinity. It's all 0. So this is 0, and at y equals 0, it's 0. So it disappears. So you get integral 0 to infinity h of y ds dy over y equals minus 0 to infinity of here, okay, g y. The y squares disappears, and so I got an s minus 1 g double prime of y ds dy. So this calculation from there comes to this point. Now, we will integrate one more time. Oh, sorry. By the way, here, h of y is dy over y squared g prime of y, not g double prime. So I put too many primes here. So even g double prime of y, only the n equals 0 term is still not there. Okay, so that's still under control. So it should be g prime of y. I was worried about this. Okay, so this is g prime of y. Now what's the integral of g prime of y? G of y? No, wrong. G of y plus constant. So a primitive for g prime of y is g of y plus any constant. I'll choose the obvious one because I want to kill the constant. So g of y, remember, had that n equals 0 term, which is 1. So the integral of g prime of y is g of y minus 1. So I'm going to integrate by parts. I can use any primitive. I'll use that. So do one more integration by parts, and what do you have? It's minus of s minus 1, integrate g prime of y, obviously, and I integrate that as g of y minus 1, y to the s, and evaluate it between 0 and infinity. Obviously, I want to kill this term, minus s minus 1, integral 0 to infinity, g of y minus 1 times s y to the s minus 1, which is s dy over y. This is fair enough, everybody? Just doing integration by parts. So now, because it's g of y minus 1, again, I plug in this infinity, this disappears, and at 0, it disappears. So this whole thing disappears. I'm trying to keep this guy on the board, okay? So this disappears. So minus, there's a minus sign outside here, minus sign here, so I end up getting s minus 1, integral 0 to infinity, g of y minus 1, y to the s dy over y. Everybody follow this? So starting from this crazy combination of h of y, I take the Mellon transform, do this double integration by parts because of this relation here. And I get that the Mellon transform of that is equal to s minus 1 times this integral, but it's right here. Um, this was not supposed to be there. Yeah, actually this is supposed to be there. Because, yeah, that was okay. So you get this. Therefore, what do we have? We have the following theorem. Yeah, we have a nice formula, right? I'll need this G double prime of Y. G double prime of Y. Yeah, okay. Did you find a mistake? Okay. So theorem is integral 0 to infinity h of y ds dy over y is equal to s minus 1 integral 0 to infinity of g of y minus 1 y ds dy over y, but integral g of y minus 1 y ds dy over y is nothing but c of s over s minus 1. So this is equal to c of s. So in other words, c of s is the Mellon transform of h of y. Remember, in Riemann's derivation, c of s was the integral of this theta function that started from 1 to infinity, and plus it had these terms 1 over s and 1 over s minus 1 terms. So all of that now has been cleanly, I think this is Polia's motivation. I can't think of any other, to try and push all this into a Mellon single function of which c is the Mellon transform of. So this is the function, not the theta function, but this modified theta function, as it were. So you use this and you get this, and now the next point is, I think I'll need this stuff. I'll certainly need this h of y. So this guy I'll need. Okay, so I'm gonna keep this, push this away. Now you recall that theta of 1 over y is root bar theta y, and g of 1 over y is yg of y. Now you're going to, and h of y has been given in this fashion, and now you have to calculate, is there a functional equation for h of y? And so I'm going to leave it as an exercise to show that h of 1 over y is also y h of y. So what do? Well, you run through these silly differential equations, then calculate it and crank it out, and it turns out it's still preserved. This functional equation is still preserved. So this is really neat. I mean, I like this. It's a very neat calculation. So h of 1 over y is actually 1 over y. And now, point number 1 is from here, this expansion here, notice that for y positive, everything is positive. The question is this positive? And so when is this positive?
So this integral representation is valid for real s greater than 1, or?
Yeah, this thing is actually valid for for all s complex. Because now h of, you see this guy is exponential decay.
Near 0, what is the behavior?
I'm gonna check. I'm gonna find that out now. Okay. So, yeah, this is analytic everywhere now. Okay. So let's just calculate first. When is this positive? So 2 pi squared n to the 4th y squared. I want it to be squared, sorry, 2 pi n squared, a y squared has to be bigger than 3. In other words, n squared y squared has to be bigger than 3 over 2 pi for all n. In particular, for n y equals 1, it has to be y squared, for y squared bigger than 3 over. So certainly, this is positive when y is bigger than 1. Because 3 over 2 pi is smaller than 1. Yeah. So this is, so observe, h of y is positive for y bigger than or equal to 1. Okay. Now I have the functional equation, h of 1 over y is equal to y h of y, therefore it's positive for y bigger than 0. By the functional equation, from h of 1 over y equaling y h of y, we see h of y is also positive for y bigger than 0. Okay, so I think I don't need this expression anymore. And what is the big deal? The big deal is h of y is non-negative. So that's the big deal. See, thus.
Or you can think of it as a probability.
Exactly. Thus, C of S is equal to integral 0 to infinity h of y to the s dy over 1 with h of y positive. And of exponential decay, because h of y has no constant term anymore. So that's, my guess is that's the real reason for this combination. Now, let's calculate C of 0. What is C of 0? Is there T now, or could somebody just check if there's? Oh, there is?
Yeah.
Okay, so maybe it's a good time to stop here, and then, now, so I'll hold you in suspense. When they have a break, so that people come back, they'll be sitting on the edge of their seats, wondering what's gonna happen next. Okay, so have your tea, and then I hope you'll come back.